even so much simpler because it differs from MSE by root, right? So simply take the square root out of it, then that's it. And then receiver sum squared, simply sum over all the observations, simply by including the sum, then you get it, right? And there's a Cedar standard error. Since we know that it's standard error, that means that I probably haven't really included variable into it, right? So I can actually calculate that. So since this is calculated by including with a variable inside it, so I need to adjust for the degree of freedom, right? So where can I get that? Well, the degree of freedom information is already included in your R output here. Yeah. So I accept that as my model output, and I insert it here as my denominator and doing the same thing, but simply taking square root out of it, then here's what I get. In R squared, you can actually get R squared from the model output, something like this. So that you can actually calculate total sum squared, right? By simply converting that, or for example, because the receiver sum squared, RS, represent the proportion of variance not being accounted for by your MS as model sum squared. So it's simply this proportion. So if this is really the basic math. And then I want to convert this back to total sum squared, the total variance. It's simply this value divided by the proportion, or simply the share of variance it has in the value that we're trying to get, which is this one, because the R squared is pretty low actually, like 0.198, right? So the remaining share can be attributed to receiver sum squared. And then if I divide it, receiver sum squared by the share, it will convert back to the total sum squared. It's very simple. Right. Okay. All right, so we will take 10 minutes break.
有时候这个资料档会压或者什么的资料，你说跟相对这个这样的，啊没有啊，你就用J图为主不行啊，会坑。你是抓这边会缺，我就那个打这个球，你就不要打这个球嘛，用别的就好。别的一样，比如说你看你这边有搜那个，看他就没有说，但是我不是有给。还是说，因为你说是什么？还是说工作？对，我知道，但是问题也是一样的。可是，我那时候听的时候，反正不存在收的这个数据，因为老师的那个数据。 新的时候还没有加，我是他这样的标准值，他这样子给你，如果这次开100万的如果你开了，没有，如果你开100万的话，就是这样做。
sure. So I think maybe you've heard about this. ANOVA, right? Being usually Stat 101, whether you, for whatever discipline you come from. You say, hey, let's do an ANOVA table or a two-way, three-way ANOVA, and that's actually quite similar to exactly what's it, not just similar to what we're talking about that in that direction. So if we put it more by the constitutional return, to put it more formally, it actually consists of the following part: the model sum square. So what is model sum square? That's the proportion variance that being explained by the variable that put into the model, right? The proportion variance being the observed value being explained by our explanatory variable. And we also have residual sum square. So it's simply the y your actual value minus the square differences of your actual value minus your predicted value, y you have, right? We also have total sum square, simply the square differences between your observed value, y, and your the overall mean, y bar, right? And its relevant degree of freedom is just, for example, the NSS is simply the total number of variables, suppose that's k, you put into the model, and when we want to investigate this particular one, so it's minus 1. And also the residual sum square is simply the total observation minus the number of variables that I put into the model. And the total sum square is simply total variance and total number of observations in the data minus the y, your outcome variable. So that's the corresponding degree of freedom that they were lost in the calculation of relevant statistic. You also see that, okay, so say I don't recognize this. What is within, between, or total, or say total effect? Okay, I fully understand this. The total variance, right, or around the total variance. But what is within effect or between effect? You say, well, the total effect, not exactly total variance. First thing I want to emphasize. And then between and within is that many of you will be doing panel regression, especially for people who come from the econ major or simply the people in political science or social science or doing cohort study or cross-national analysis. So you have this kind of data structure, for example. I'm doing a cross-national study about what specific attribute are more related or less related to being infected with COVID, right? So I'm doing I got this huge funding from the WHO, and I surveyed 10 countries, got a total of 6,000 observations. That means each observation is nested within a country. So maybe you gather, say, 300 observations from Taiwan, right? And then 1,000 observations corresponding to population size, 1,000 observations from the US, and 5,000 observations, there was too much, 2,000 observations from China, right? So that each observation is nested within some higher level unit, say country, right? So there's definitely huge differences in the infection rate across country. But here, what will be interesting is that we want to see what personal attribute and also some country level attributes, some country level variable, personal variables. If the person is nasty, so if you have a couple observations, so say 10 person are nested under a higher level unit, say country, those observations all come from the same country. Then they share some country level value, right? So how do you say? They come from the same culture, they have the same race, and even they could be of the same gender, right? So there doesn't exist some cross-level interaction. There's a cross-level variance, so to speak. For example, you say there are a certain amount of error that can be attributed to this higher level unit country, or some element some variance can be attributed to personal level, say whether that person like to wear a mask or others don't. So no matter who he is, or his genders, and his the genetic value, and whether he has been vaccinated, he always had higher probability of being infected with COVID. But there are definitely some say, because for the national government, all they really want to tell is that whether policy work or counter COVID policy is more effective in other countries. So there's definitely some variation at the country level, means that the effect vary across countries. So that's why we call it between effect. Between effect, so to calculate between effect, we simply calculate the group average. So, for example, if you can say whether the same policy or the counter COVID policy work better in China compared to U.S., then you simply calculate the infection rate across all the population surveyed in China compared to the so that the value you will get is just a group mean or national mean, right? So if you survey 6 countries, you will get 6 group mean or national mean. Compare the value to the U.S. average, right? And that would be the between effect. Means that the between group variance. So what's the within effect? So within effect is that the amount of proportion variance that can be attributed to unit level, the basic unit level. So here I want to see some personal counter COVID measure. If that's more good, so does that work? For example, like wearing masks. Some people in Taiwan or China also don't want to just don't have the habit of wearing a mask. So they also have higher probability of getting infected. So how much observation in a group deviate from grouping? So you can say you want to make this inference on data, draw the inference on data. Say, okay, so even though at first glance the infection rate in Asia is much lower than what's being observed, it's being calculated that the group being the U.S. or Western Europe, European country. But within Taiwan, those observations that don't like to wear masks, they seem to have higher infection rate that deviate from the group B, the Taiwan B, or the China B. Does that make sense? So that's the within group variance. So whenever you're doing that panel study or panel regression, it's always the variance always comes from 2 sources between them within, and combined they form the total effect, total variance. Okay. But here, since our usually like in those simple regression data, we do not distinguish there's a higher level unit, so we do not need to care about that. At least by now. So here, that's pretty much our friend. Can you deduce the sample size? So I have this. So you can tell it's just a univariate regression with only one explanatory variable, correct? Or the response, the y variable is cell, right? So we have this residual and degree of freedom from the calculation of this variable on its relationship with this cell. And also you shouldn't forget to add 1 into it because there's also another your dependent variable. So the sample size should be 398 plus 1 plus 1 should be 400, right? Can you calculate the TSS? You say, hey, I don't have those information we just had, like 10 minutes ago. I don't have receiver, I don't have those receiver sum square. I don't have model sum square. How can I calculate that? Well, they're here. So if you add it up, then you will get the TSS. there's something that you haven't heard about, F-statistic. But before that, we quickly jump to our stuff. So doing ANOVA. So ANOVA table is very easy to generate. It just simply type ANOVA and then enclose that. You enclose your model output, and you will show what I just showed you. Or you can do using the AOV function, analysis of variance, by simply specify your data, or simply just like what you were doing in LN, linear regression model. Specify your data source and your Y variable and your X variable. Then it will show you relevant analysis of variance information. Or there's or you can simply that is exactly what I showed you. Okay, so let's get back to our F statistic topic. So hey, I know T value and stuff, but what is F statistic? Or is a statistic pertaining to the joint test of significance. So if you want a fuller explanation, you can just want to take it to Wikipedia page, even though I won't be talking about it, that's irresponsible. So that's exactly similar to what you would do when doing hypothesis testing, because here, if you, the circumstances that F statistic what we code for is that you want to, if you're testing a multivariate regression, meaning that regression was multiple variables, more than one, right? And you can now assess this null hypothesis against alternative hypothesis one by one, how we keep this. And so here you only want to test is so you specify a 10 variable regression, 10 variable multivariate regression. Say, I'm not doing this in vain, like this is just pointless because all the variables are insignificant, so they're pretty much like trash, right? But of course, you don't want to see this, so you want to make sure that, okay, now this, one of the variables I throw into the model is significant. So here is how the F statistic count works. So the null hypothesis is that, okay, so for all the variables, the n variable I throw into the model, that is, one of them is significant, meaning that it's non-zero. Right? So that would be my alternative hypothesis, meaning the hypothesis that I prefer, I prioritize. So you evaluate this against the null hypothesis, meaning that, okay, so all the variables you throw into the model are pointless. It's just it has no relationship with the outcome variable. So it's simply calculated as a ratio between NSS over residual sum squared. So if over residual sum squared is okay, so your model cannot explain anything, then this should be larger, right? But if the variable that put into the model is good, that means that NSS model sum squared should explain the major variation in a dependent variable, and also they need to be adjusted by their relevant degree of freedom, right? So that's why it's here. So usually we reject null hypothesis if F is statistically larger than some specified value, some threshold value. Otherwise, we should admit that okay, so I'm doing the Horber model. The model is fit poorly, and I should admit that okay, the null hypothesis is true, meaning that there's no relationship for all of the variables in my model. So what would you say about if statistic is clearly very significant? So, but we only put one variable into it. So there's that makes sense. I mean that variable makes sense. It does have some effect on it does somehow coordinate with the dependent variable. Okay, so last topic we're talking about bias variance trade-off. So to do that, we basically we should first load the advertising data into our environment, and then we will compare estimated coefficient, standard error, R squared, and relevant F statistic. So those are saved in our shared Dropbox, so you can download it here. So here's a couple ways that you can download and also save data if you want to use later when your own device. So here, you can simply load this data as a CSV because the data is saved in CSV. So I mean, usually for those open source data, the owner of the data or instance is open to you. So he or she will usually specify the type of the data. Say, oh, it's a public data, so that will require you to do first processing on some third-party software, for example, like Apache or something. Or you say, oh, it's a CSV. I made it easy. The CSV in Excel, so everyone can download it, and that's good. So here I specify the CSV. You should also know that that's the way how R repackage read data that's stored in different format. Say that CSV, mean that it's a still. If you read read table, that means that the data is stored in Excel format. If you read DTA, it means that the data is stored in data format. Right, so you need to convert. Chances are, or sometimes you really need to convert those data, or have someone convert the data for you. So, but that's you can only acquire those skills learning by doing. There are right. So how to what load this data other source, or if I store it somewhere. So for example, this it usually begin with your own device. So here you come from some web domain, right? Because we come from my own Dropbox share folder, so I simply specify this way. And there are times when, especially in those RDS data, because R also has its own data format called the RDS. And if you want to download data from some web-based source, sometimes you will need to enclose your web domain inside URL and your web address, and then enclose with the data format. For example, read CSV, DTA, or simply read RDS. Ensure that it's R's own data format. Shouldn't be is actually not preceded with a dot. And also it should be reading capital letter. And there are other ways. For example, sometimes you can actually make it easy. If you only want to your tasks that are processing at hand only require you to work from a single directory, your file directory, say, hey, my D folder. Then you can actually tell R to set by working directly to this folder. And so for the following command that you put in referring to R, you will read file from this particular folder. Does that make sense? But after you type this command, if you also want to access file from other folder, then you won't get into that. So I usually don't use that. Right, so you can have a quick summary to see the quantile distribution of advertising data. Right, check out the dimension. But the rather small data is only 200 observations, 5 variable. And there's another quick way to know what's inside data. Simply type str, structure of the data. See that, okay, I have this following variable, right? And the variable type, so the first is an integer, then the four others are numeric, UAN. So I have 200 observations, 5 variable. And also display the first couple observation value for this variable. Now, since R is just row number, so it's not important to us, so we can actually take that out by, quick reminder here. So here's so whenever try to access a particular entry in the data, this would be, so for example, your data frame, the data frame of matrix object, you should point to the particular entry on the Greek-like structure. Suppose you're on the structure. Something that you have row, column, right? So if you want to access the data point that's on the second, let's say that's on the second row, first column. Here. So here's the column. Second row, first column. Put it here. But here, because I don't want to remove the entire column from the data, the first one. So I simply put it on the column cell, -1. So you will remove first column of this data. Okay. And then I can also rename the data. And this is actually a good thing. Is that okay? So if I want to do some preliminary analysis on data, and I do not want to override the entire data. So we can do this a little short. For example, okay, so I keep this data and then I rename it. Because I have to already do some change with the data by removing the row label on the data. So I rename it to new data, right? And that's a good thing because you keep this, or actually you preserve your original downloaded data, but you also have this modified data. So you actually have two of this in your memory. So maybe like once, maybe just a couple minutes time, you're not really happy with the modified data. You still have the original one. That's good. But here, because I already know what I'm doing, so I rename it. So I rename this new data to this original name, but you don't necessarily have to do this if you have all the use for it. Especially when the data is, you're working on a big data, it's tricky lots, so it takes some time to download it from a third-party device, and then you just override it with something that, right, so it's going to take a couple hours for you to reload this data. That's bad. So you see, the first column is already removed from this modified data. So I know what I'm doing, so I attach this data so that I don't need to type that much. So I can compare different model fit, right? So the first one is a univariate regression. The second one is a bivariate regression of a TV newspaper. The third model would actually include 3 explanatory variables. But before that, we'll go back to our lecture slide. So how to compare model fit for different model specifications? This model fit, in terms of R-squared, improve through an increment in the number of explanatory variable that we add into the model. And how about their X statistic? So we can first plot it out, right? Plot the predicted value on the various scale plot between scale and TV. Well, it's actually a very tricky question because it's hard to answer. Because regression, we tend to think that regression is more like curve fitting. So we try to plot the regression line as I do. We used a 3-dimensional graph last week. Try to plot the regression surface. We're trying to be singular in multi-dimensional space. Then minimize the square distance of all data points, some square distance of all data points away from the predicted mean. Right? And the surface that minimize this total some square differences between the estimated mean and all the data points is the class linear predictor. So that's why many statisticians tend to think that stats are about curve fitting. To fit a curve that captures much of the major variation in the data. But errors usually come from a couple sources. So we can actually decompose this part, right? Because x times beta is just beta hat, right? It is a beta hat plus random error here. So the variance actually comes from three sources. It's a variance of the predictor itself, predicted value itself. Also the bias. Bias, so where does bias come from? Bias is the amount the error beyond the random error that we wouldn't be able to capture in a relationship between our predictor and the outcome variable. Meaning that, so we try to, because the way that we put a particular model, and we put a particular variable into a model, is that because we think it's relevant to the outcome variable of interest. You think it's somehow correlated with y, right? And in that sense, mean that you're trying to delineate one of the dimension of the outcome variable. So suppose you work into my say my office, and I put a picture in front of you. So that's a human. Right? This is a human. I say or ask you to put variable to delineate this object. So you do that. Okay, that's a human, right? So I will first put so what specific attribute does the human have? You're trying to define someone that you don't know that much. Gender, right? Height, weight, and some undefinable feature, personality, or race, right? Hair color, eye color, right? Well, because all these features are what you think would be correlated with the object that you try to make prediction of, right? So that's the source of bias, meaning that the variable you put into the model does not really capture the underlying relationship of the explanatory variable and the outcome variable. So suppose it said, I'm asking you to put variable that or how this to be inferred to define a person. But you actually insert into some value, for example, like metric ton or something that you use to measure a hard object. And I would say your regression simply missed the mark. And the variance of the predictor cell, of course, is the part of the error now explained by bias. Right? Just like the residual sum squared. Right? Or the sigma squared, just irreducible error, meaning that no matter how good our model is or how many variables we put into the model, there's still going to be a certain amount of error that cannot be explained through model specification. Specification means that the number of variables you put into the model, what you put into the model, and their functional form, meaning that how they are related to the outcome variable. For example, you said, x has a curvilinear relationship with y, so I should put the square of x. Right? Or maybe the relationship is guided by some natural log function, something like that. So here I give the full definition of that. So bias is an error comes from erroneous assumptions in learning algorithms. And eventually, in just a couple of weeks' time, we'll be doing some machine learning, statistical learning. So that's the erroneous assumption that some variable is correlated with the outcome variable of interest. And in engineering discipline, we should call it the feature, call it variable feature. So if I ask you to delineate a person, so what feature does that object has? So it could be like height, weight, race, hair color, eye color, right? Things like that. And this shortcoming is generally termed underfitting. As I said, perfitting, and if you fail to capture this major amount of variation, called underfitting. Say, hey, since we have underfitting, so it must be something that's over, right? We're doing this too much. Well, we do have it. It's called overfitting. It's called the confounded variance part, the variance of the predictor itself. That happens when you error confounded sensitivity. You have a model that's too sensitive to small perturbation in data distribution. Well, because if I try to capture as much variation in the data as possible, like here, right? So you might working too much by keep fixing your data, by keep adding a square term or multiplicated interaction term, or using log normal or natural log function, or put others on penalizing function, for example, like that's a linear absolute regression operator, for example, we will be learning that in a couple of weeks. So your regression line should probably work like this. The first going down, going up, going down, going up. So pick up almost all data points in the data. I mean, that's very sensitive to the variation, small amount of variation in the data. To the point that it almost explains, say, 99% of the data. So you have really high R-squared. So you're saying, okay, so that's a very good model for this particular data. But I would say, so you're doing this for for a company, and the company wants to put this there to sell. So if suppose you're predicting the major variation in the stock market for a particular type of a future, I mean, it could be crude oil, or you're done from the foreign exchange, the Russian ruble, right? Which is falling right now. So your company wants to take this as a product and sell to a customer, to a client, for a forex trader. Say, hey, I want to use the model that I trained on Russian ruble to bet on Japanese yen. Well, they probably will be a poor fit, right? Because your data are trained, which means we have to use the word model tuning. It's so fine-tuned to this particular data set, that those small amount of variation in this data set. So you were entirely missed. You cannot detect major variation in other data. And also, note that, so given that this part is usually taken as a constant for the value, so that means there's an irreducible part. So no matter what we do, this irreducible error will still exist. So we're still taking that as a fix. So that means for fixed amount of variances, you will have some sort of seesaw effect, right? If this part goes up, the other part should go down. If this part goes up, then bar should go down. So that's why we call bias variance trade-off. Let me refer to the problem that we encounter when trying to train the learning algorithm to try to minimize expected generalization error with respect to a particular problem. And that's something that we need to take care of. I'll illustrate this, and before that, right, you can try to think of the situation where that's quite relevant to what the people living in Kiev is doing right now, right? Because they actually, the government, the city government of Kiev have been distributing a reserve rifle to all the able-bodied male citizens. Oh, I'm not sure if they actually give that to a woman. It probably does. But seems that they actually encourage women to get out of this country. And only keep men, fighting. Right. So suppose you're one of the able-bodied men, whether you're a man or woman. Right. So you're so motivated by your high sense of patriotism and want to protect your homeland. So you go to those this arsenal to pick out a rifle that was given randomly to you. Right. That's exactly what I encountered, because I was saying that nowadays they don't have conscription military service. It was actually abolished a couple of years ago. So I was a reserve officer when I was studying here, and so I was assigned to training camp, the second lieutenant. So we actually do this quite often. So whenever there's a new batch of rookies that come, is it fresh coming out of college or high school and they're getting to the military camp, and we need to teach them how to shoot rifles. And since those rifles are given random, so we need to test fire, right? So we use this example to illustrate the bias variance trade-off. So if you're given a rifle, then you put on a target, you align the front, so that would be the rear side and the front side, right? So we're trying to assess how accurate is this particular rifle. So we're saying the first one is pretty good, right? It's right on the spot. Right? So that's a good rifle. So what about the second one? It seems that the point of impact, you want to know what point of impact is? Yeah, let me write this down for you. I suppose, yeah, I think this is. So that means where your bullets are hitting the target. I think that it's still quite good because the point of impact is distributed with some regularity. Roughly circle, right? But this one, the third rifle, you see that is a little off, right? But in a systemic way, right? Let's say it's still pretty accurate. It only needs some adjustment, right? And this is how, for example, you probably need to fetch a tool and readjust the front side of this rifle, right? So we say if you want to go and fix your point contact down, then you would do some clockwise. You use the screwdriver to roll this clockwise. You will put it up, then you would need to do like counterclockwise, right? So how about the fourth rifle? Last rifle. It's not only off target, but it's more scattered than the second one. And I would say it's a better rifle. It's of no use. Let's throw that away. Personally, change to better. Right. So they have to explain the variant because it's more scattered. Means that it's more your prediction is more varied. And also you also miss the mark compared to this one. This two top of this graph. Right. So we can actually work this out in R. Right, so we previously fit 3 model, right? So we can define a function to calculate the bias variance trade-off. So here we first calculate the bias. So bias is just the variance of the predictor itself, right? Means some square differences. So here, this is how we wrote the function in R. So we first open out the function command, right? So if you wrap the function command on say model output or a variable in data set, that won't work, right? Because whenever you open the function command, you're actually telling R, I will define a function here. And those are the value that will appear in the function that we need to calculate by, and that we need to generate the value that will be generated from the function this way. And those values should appear in the exact same sequence as appear inside the curly bracket. Right? So whenever you put the function command, you put what kind of data that should be inserted into the function. So here I said, the first one that appear in the function command would be predicted data. So the bad thing is, if somehow you forget the sequence, and then so after you define your function, you put the actual value first, followed by predicted value. Ours still work. It will still work. It will still